Okay, this is the summary of the sixth lab in which we have studied linear position force application sensors. Basically, the sensors which are used to detect the change in position or which are used to detect the force. Basically, distance is mandatory to find the force, as you know that force is equals to ma, and acceleration is the distance per unit square. So if you know the distance, you can simply calculate the force. So basically, these three sensors will be used to find or to measure or to sense the change in position, so that the distance can be found, and through the formula you can find the force as well. So first we studied a linear variable differential transformer that you people already have studied in the control system, I guess, in the previous lab. It is a transformer, so its working principle will be same as a normal transformer, i.e. the transformer action. The mechanism is the transformer action, as it is the summary, so I won't be telling you each and every thing. Just making this video for those who want to revise what you have studied in the lab. So this is the construction of the Lvdt. It consists of a primary and two secondaries. Secondaries are connected electrically, while primary and secondaries are isolated electrically. These are magnetically connected, just in the case of normal transformer. Well, its working principle is a bit simple. As you know that this and this secondary winding is connected in series, and by this way, this dot analogy is used for the live terminal. For example, if this is the dot, it indicates that this terminal will be live and this will be neutral. Similarly, for this coil, this is the live and this will be neutral. So it is connected in series by this connection, live with live, and the neutral is left. Similarly, the neutral is left here. So the connection, if in case of DC, will be equal to this, when the positive is connected with the positive and two negative terminals are left behind. So in this case, the total the voltage across these two terminals will be equal to the difference of the individual voltages. Same is the case here. When the core is at the center, the equal amount of EMF will be generated on this and this secondary, which will sum up to 0, because these will be subtracted, VA minus VB, and their sum will be equal to 0. When the core moves forward, the generation in this secondary increases because of the core, because core maximize the generated EMF, because it through the core the rate of change of the magnetic flux will be maximum magnetic fields will interfere with this secondary winding due to this core. So VB will be greater than VA, so the generated output will be negative, and when it will be moved backwards, in the core will move through the VA, then the VA will be greater than VB, so the difference will be positive. So on the basis of the output generated, you can find the change in position, or whether it was the forward motion or the reverse one. You can find the direction of the movement as well. So as it is a transformer, so it will be given an AC, not a DC, because DC transformer do not operate on the DC, as you people know. So to give it the input, we use oscillator, a 40 kilohertz sine wave oscillator. It will provide a sine wave of 40 kilohertz frequency to the primary. The output will be generated across these two terminals. The output will be amplified and then filtered, so that you can filter out the low frequency noises if it appears. Then after filtration, you will use full wave rectifier, and then you will find the result. So basically, first of all, you will set it to 0, and then you will rotate the knob clockwise to move the core to the forward direction, and you will keep checking the generated voltage. Similarly, you will rotate the knob backwards, and you will check the generated output, and you will just make this table. Similarly, next we have linear variable capacitor. You people will have the idea of it if you understood pin photodiode. As in the pin photodiode, we said that the intrinsic region between the P and N region acts as a dielectric, and the P and N act as the plates of the capacitor. So by addition of the intrinsic region basically increase the distance between the plates, so the capacitance decreases. So same is the case here. Not exactly the same, but the mechanism will be same. The plates will move forward and backward, which will affect the capacitance. Therefore it is called linear variable capacitor. These plates will move forward and the capacitance will increase. This plates will move if backwards, the capacitance will decrease. So minimum capacitance you can obtain from it is 25 microfarads and maximum is 50 microfarads. The internal circuitry of linear variable capacitor circuit is like this. It is a resistor connected in series. You will give the AC input, and you know that in case of capacitor you take reactance, and reactance is equal to 1 over 2 pi f. So basically when the capacitance is increasing, the xc is decreasing, so the voltage drop across the capacitor will decrease, and while we are obtaining the output across the resistor, so it will be if it is decreasing, so it will increase. Similarly, when the capacitor decreases, the xc will increase. Xc will increase, the voltage drop across the capacitor will be increased, while in the case of resistor it will decrease. So basically the change in position affects the capacitance, capacitance affect the reactance, and so the voltage drop across the capacitor or the resistor is affected. Just take an example. For example, if I move the two coils in the forward direction, then the capacitance increases. Capacitance increase while the xc decreases. Xc decreases, it means the voltage drop across the xc is decreasing, while the voltage drop across the r increases. So in this manner the output is taken across the r. So when you move forward, the voltage drop across the r will increase, but it will not be decreased to 0. But for the good sensors, we know that the initial reading should be 0. To make it 0, we will use the differential amplifier. What will it do? You can take the minimum output coming from this sensor, you will give it as an input to the differential amplifier, while the second input will be given through the potentiometer. We will change the potential of the potentiometer until the output of the differential amplifier is 0. This is the calibration, and after it is given you the 0 drop, then it means that it is calibrated, and after that you will start taking the calculation by moving it forward and backward through the same knob, just as this. It also has the knob. Then we have a strain gauge. Strain gauge again is a simpler in composition. Its base is non-metallic, and on it you have a metal wire. The base is elastic. Similarly is the metal also is a bit elastic. When it is stretched out, the length of the metal increases, the length of the metallic wire increases, while the cross-sectional area decreases. So it increases the resistance of the strain gauge, and so basically you can find the change in resistance because it is basically you can find the strain because it is affecting the resistance of the strain gauge. So to use it in a circuit, you use either this configuration of the Wheatstone bridge or this. In this configuration you need one strain gauge and 3 normal resistors. You will press or stretch this strain gauge, and the output across these two terminals will either increase or decrease depending upon the overall calculation, and depending upon the resistance, if it is changing or if it is increasing or decreasing, the output will also be affected with the change in resistance of this strain gauge. But as you know that this bridge is needed to be at null point at the start, so that the initial reading is 0, but you can achieve it only at one temperature, because all the these 3 resistors are carbon resistors and this strain gauge is of metal, so the effect of temperature will be different on the strain gauge and the normal resistor, जिसकी वजह से you as for example, if you will set it at 0 deflection at one temperature, but when the temperature increases, the temperature of these 3 resistor will increase differently than this, so the null point will be affected. So and the second drawback of this configuration is that output is very low. First, effect of temperature is greater on this configuration, and secondly the output is very low. To correct these issues, you use this configuration in which you have all 4 strain gauges. So the effect of temperature is minimized now, because effect of temperature is now equal on all the resistances of this Wheatstone bridge. And secondly, the output will be doubled, because these two strain gauges will be dummy strain gauges, while these 2 strain gauges will be active strain gauges. So these two will be pressed or relaxed, compressed or relaxed uh, at the same time. So the output will be doubled. In this case, only this one was uh, either stretched or compressed, while in this case both will be stretched or compressed at the same time, so the output will be doubled. So both issues are resolved in this circuit. Moving towards the apparatus. So this is the linear variable differential transformer in this trainer. You can see these 3 coils, just like the configuration that I have told you on the board. When you move the knob forward, the core inside it moves forward, and when you move it like anti-clockwise, the core moves backwards. This is the input will be given through the oscillator. This is the oscillator, and then you can see that at the end of this assembly they have connected the variable capacitor, because as you know that the core is moving forward and backward. They have simply connected another plate at the end of this axle or this core, so that you can take the advantage of लीनियर वेरिएबल कैपेसिटर टू, मतलब आप उसको लीनियर वेरिएबल कैपेसिटर के तौर पे जगह बचाने के लिए इन्होंने इस्तेमाल यहीं पर एक असेंबली में इन्होंने कनेक्ट कर दिया। तो बाकी प्रोसेस वही है जिस तरह से बताया था कि आपने सबसे पहले इनपुट यहाँ पे देनी है, आउटपुट यहाँ से, then you will filter it out, then you will rectify it, and you will display it, and you will move it like this. This is the strain gauge. You can see here it only gives you 2 terminals, minus and plus. These 2 terminals are basically these 2 terminals where you need to connect the galvanometer. As we don't have a galvanometer, so we use instrumentation amplifier instead of it. So we will simply connect, if you see here, this is the strain gauge. You will connect the instrumentation amplifier, and then another amplifier to increase the gain, and then you will display it. And when you turn it on, see, when it is pressed, the output voltage increases or decreases depending upon the load present on it. Secondly, one thing is different in this trainer. Lvdt and a linear variable capacitor are on the same module, the same slot, on the same package, while in this case this is the Lvdt and variable capacitor is given at the different slot, while the mechanism is same. You can simply make the circuit from the manual, or because right now I don't have time to make the whole circuit and show you the working. So this was all about the lab 6, in which we have studied 3 instruments or sensors: Lvdt, a linear variable capacitor, and strain gauge. Thank you so much.